Welcome to the debate. We are diving deep today into open vocabulary segmentation, or OVS, which is really a critical challenge in computer vision. The basic goal of OVS is to partition an image based on, well, pretty much any free-form text concept you can think of. It pushes way beyond the traditional limits of, predefined fixed classes.
And this really represents a kind of collision point for two distinct architectural philosophies in modern AI. So on one side, you've got models like CLIP. These are built on this massive scale contrastive training, right? And they excel at global vision language alignment. But when you need that precise, dense spatial localization for segmentation, CLIP often, frankly, falls short.
Exactly. And then on the other side, you have models like DINOv2. Now, these are purely visual, self-supervised networks. They're designed through really intense pre-training to generate incredibly fine-grained, rich spatial encoding. They often use things like attention maps to inherently sort of delineate objects and scenes. The problem, though, is that DINOv2 just by itself is, well, fundamentally incompatible with natural language concepts.
So the source material we're getting into today proposes this talk-to-Dino architecture, and it aims to be the definitive solution to this duality, this problem. It claims to fuse the spatial localization mastery of DINOv2 with the semantic understanding of CLIP. And the central mechanism here is a novel, learned, nonlinear mapping function, a projection, essentially, that tries to bridge these two fundamentally different embedding spaces.
And that is precisely the core of our debate today. We're really asking whether Talk-to-Dino's hybrid approach, which relies on this specialized nonlinear projection and a rather clever mechanism for selecting visual features, whether it truly represents a foundational, superior architectural paradigm for OVS, or, as my colleague here suggests, is its effectiveness primarily derived from just optimizing the, let's face it, exceptional quality of the pre-existing DINOv2 spatial features.
Right. I tend to come at it from a slightly different angle. I believe that Talk-to-Dino is an incredibly efficient layer, sure, but it's built on top of arguably the strongest visual backbone we currently have. Its success, I think, is heavily indebted to the specific sort of innate feature properties of DINOv2, making the projection more of an optimization rather than a truly necessary generalizable design shift.
And I'll be arguing that the learned projection is crucial, it's novel, and it's highly efficient. It represents, I think, the essential architectural synthesis required to actually transfer those high-level language semantics down to the fine-grained visual features. And it maps out a path for efficient cross-modal dense prediction in the future. Okay, so to start, let's talk about the architectural necessity of this bridge. When we talk about CLIP's text encoder, we're talking about a textual embedding. Let's call it T. It exists in a specific high-dimensional space, say DT. And this embedding, it basically summarizes the entire text prompt's meaning, right? DINOv2, meanwhile, provides these dense visual patch embeddings, V, but in a different space, DV. Since these spaces were learned totally separately through image-text, contrastive learning, DINOv2 through self-supervised tasks, they're often dimensionally different and semantically uncorrelated at that fine-grained patch level.
They're like neighbors who speak completely different languages.
Exactly right. You need a translator. And the core novelty of Talk-to-Dino is this nonlinear warping function, psi of t. This function is composed, actually quite simply, of just two affine transformations. You can think of them as matrix multiplications, separated by a hyperbolic tangent activation. Now, this nonlinearity is, I argue, critical because it forces the transformation to be complex enough to map the abstract global semantics of T into the highly localized, nuanced semantic space of V. And this method, crucially, is also computationally efficient. It requires minimal learned parameters compared to some competitor models that demand, massive external knowledge bases or fully trainable visual components.
It's a compelling argument for the efficiency, I'll grant you that. But I'm sorry, I just don't quite buy that the nonlinear complexity itself is the crucial part of some paradigm shift. The ablation studies in the paper seem to challenge that necessity. I mean, if you look at their comparison of projection types, replacing that complex nonlinear projection C of t with a remarkably simple linear projection, just one matrix multiplication, it only results in a pretty minor performance drop across many of the benchmarks.
But even a minor drop, wouldn't you say, validates the nonlinearity's role in enhancing the semantics?
True, true. A drop is a drop. But the minimal nature of that drop suggests, to me at least, that the DINOv2 space is already intrinsically highly amenable to CLIP's semantics. The success seems to hinge more on the quality of the features you're projecting to rather than the specific complexity of the projection function itself. And, this leads directly to a really vital point about the backbone dependency. The model's performance is deeply, deeply dependent on the specific DINOv2 variant used, specifically the one trained with registers.
Okay, let's maybe clarify what we mean by registers for anyone listening.
Sure, of course. So DINOv2, particularly the VIP models, often uses these dedicated register tokens during its pre-training phase. These tokens are basically designed to soak up background noise and prevent the attention maps from getting corrupted by extraneous artifacts. This becomes especially important when you scale up to the larger models like VIT-L. This architectural feature, it acts essentially as an innate data cleaning mechanism built right into the pre-training. And the source material shows pretty clearly that without these registers, especially for the larger VIT-L models, performance degrades quite significantly. So that dependency really highlights that the success hinges on the backbone's pre-trained spatial quality and this built-in data cleaning, maybe more so than the proposed language alignment method alone.
Okay, we can certainly agree that DINOv2's inherent quality is foundational, but that quality is, well, inert for OVS without language, right? This leads us, I think, to our first core disagreement, the effectiveness of the selective attention alignment strategy. Talk2Dino doesn't just project the text embedding, it intelligently uses DINOv2's own attention structure during the training process. See, DINOv2, being a transformer, generates many different attention maps. There's one for each attention head, AI. And since different attention heads tend to specialize, one might capture an object boundary, another might focus on texture, just averaging them all together would likely dilute the specific semantic signal you want. So Talk2Dino exploits this. It computes many similarity scores between the projected text embedding, phi-t, and the visual features weighted by each individual attention head. And then, crucially, they use the maximum similarity score for their InfoNIS loss calculation.
Right, InfoNANS, or noise contrastive estimation. That's just the standard mechanism for contrastive learning, yeah? Pulling positive pairs, the matching text and image regions, closer together and pushing negative pairs farther apart in the embedding space. The complexity you're highlighting is in map maximization step. Now, while you champion this use of the maximum similarity score across all N attention heads as key to localized robustness, I find it structurally a bit risky. Doesn't relying on just a single maximal activation, the single loudest signal, if you will, potentially introduce noise. Or maybe it just favors the strongest global feature, rather than guaranteeing a truly precise localized segment.
While the ablation tests presented seem to show that this maximization strategy delivers superior localized results compared to simpler techniques like standard averaging, especially when you look at the more complex benchmarks. The goal isn't just to align the whole image globally, but to find the specific spatial subset that best matches the caption. By maximizing, the model dynamically selects the specialized attention head that hopefully perfectly corresponds to the specific text query. That maximization, I argue, is the elegant mechanism that enables the localized bridging we're looking for.
I understand the empirical result, yes, but is it truly localized down to the segment level? If we look closely at the paper's supplementary analysis, their attempts to align individual words, the finer text tokens, to those attention maps actually failed to improve performance over just using the standard CLIP CLS token. And the CLS token is, CLIP's powerful global semantic summary. So this, for me, reinforces the view that the heavy lifting is still being done by DINOv2's high-quality dense features, and the alignment is still primarily leveraged by CLIP's global intent, regardless of the complexity of the maximization step.
I'd push back on that, because the innovation is precisely in maximizing the match between that global semantic intent from CLIP and the best spatially coherent representation DINOv2 can offer for that intent. But okay, let's pivot maybe to our second key point, efficiency and the comparison to competitors. Talk2Dino achieves undeniably state-of-the-art results while being dramatically more practical than some other approaches like, say, Frida or ProxyClip. For instance, it requires no external knowledge database like Frida does. And, maybe more importantly, its visual encoder stage is far smaller and requires significantly less computation. We're talking about something like 86.6 million parameters for Talk2Dino, compared to competitors sitting closer to, 172.8 million? This, I think, proves that an efficient learned projection is a cleaner and architecturally superior way to inject language semantics into this localized visual space.
Okay, while the parameter efficiency during training and the smaller architecture size are certainly commendable, we absolutely have to acknowledge the complex inference overhead. The high benchmark scores, particularly on some datasets, rely quite heavily on a highly specific multi-step background cleaning procedure, and that procedure is, well, it's not trivial.
But you could argue that procedure is an architectural necessity driven by DINOv2's own innate characteristics, couldn't you?
Precisely my point. DINOv2, because it's trained using self-supervision, is exceptionally good at finding coherent foreground objects. But in OVS, you need to confidently segment out the background noise, too. So this background cleaning procedure they introduce, it requires calculating a whole similarity matrix relating all the potential classes to all the attention heads. It then averages these attention maps in a specific way and uses a mixing weight, another hyperparameter, lambda, to shape the final similarity map. It's quite a multi-step process, and it's crucial for achieving those top scores reported, particularly on datasets like Cocoa Objects and Pascal-Voc.
I see it as an efficient post-processing step. It leverages DINOv2's strong attention heads specifically to sharpen the mask fidelity, maximizing performance where simple thresholding would likely fail.
Perhaps, but I would frame it slightly differently. The very need for such a complex post-hoc cleaning procedure suggests, maybe, that the projection psi of t and the maximal alignment during training aren't quite sufficient on their own to create a perfectly clean semantic segmentation map. It feels like it still relies heavily on DINOv2's known ability to highlight foreground regions to kind of fix residual semantic contamination after the main mapping has already occurred. And this reliance, I think, leads us neatly into the crucial final point, the generalizability, or maybe lack thereof, of DINOv2's feature space for this method. The study itself shows pretty starkly that if you try to apply the exact same Talk2Dino training pipeline to other strong self-supervised visual backbones like MAE or even the original DINO model, the whole system just kind of collapses. For example, the same ViteB model that scores, in the high 80s MIOU on DINOv2, it drops to below 30 MIOU when they try to align it with the original DINO backbone. That suggests the successful bridging is highly specific to the semantic richness, the particular self-attention properties, and yes, the use of registers in DINOv2.
But isn't that specificity precisely the strength? Doesn't it reflect an intelligent architectural choice? Talk2Dino identified arguably the optimal visual encoder currently available for localization, that's DINOv2, which provides superior patch-level semantics, confirmed by things like patch linear probing accuracy in their own tables. Since this fusion architecture is designed specifically to handle dense prediction, doesn't it make sense to tailor the solution to the backbone that offers the highest quality, most localized feature map? This approach is, I think, about optimizing for the reality of the available tools. The necessity of registers, which we discussed earlier, simply highlights that DINOv2's features need to be used correctly, with their specific properties in mind. Talk2Dino developed a tailored mechanism designed specifically to exploit DINOv2's high-quality attention maps. And that's why it maintains robust, consistent performance across different VIT sizes, from small to large, where other hybrid models might struggle.
I understand the argument for tailoring the solution to the strongest component. However, wouldn't a truly foundational architectural paradigm shift show at least some degree of transferability or offer some structural insight that applies across similar models? When the Talk2Dino structure fails so dramatically upon attempting transfer to very similar self-supervised architectures like MAE or the original Dino,
it strongly implies, to me, that the real novelty driving this success lies not so much in the bridging mechanism itself, but rather in the pre-trained data cleaning and the highly successful self-supervised objectives inherent to DINOv2.
But surely that richness in DINOv2's visual space is functionally inert for the task of OVS segmentation without that language alignment. The nonlinear projection and the maximal attention head selection successfully make that connection, defining an efficient and effective fusion strategy.
Yet, the continuing dependence on those architectural cleanup details like the registers and that complex background cleaning procedure, it suggests that even after the projection, the semantic gap still requires a deep reliance on DINOv2's innate localized encoding properties to really sustain those top benchmark scores.
So, to summarize my position, Talk2Dino's learned nonlinear projection, when coupled with the maximal attention head selection, successfully creates a precise semantic bridge between language understanding from CLIP and DINOv2's fine-grained spatial features. This novel architecture provides, I think, compelling evidence that merging vision-language capabilities and self-supervised vision via an efficient, learned mapping layer is probably the most fruitful direction for future cross-modal and dense prediction tasks. It really defines a highly efficient, high-performance way to synthesize these distinct pre-trained models.
And my conclusion remains that Talk2Dino is an outstanding piece of optimized engineering, one that leverages the absolute best localized visual features currently available. The impressive results, including the strong performance enabled by that background cleaning procedure, which, again, relies heavily on DINOv2's inherent foreground focus, these reinforce my view that the success is primarily rooted in DINOv2's inherently superior localized encoding. So, while it's excellent work, experts should remain cautious about whether this constitutes a truly new general paradigm for language vision bridging, or if it's simply the best way we've found so far to exploit the unique specialized feature space of DINOv2.
Well, regardless of exactly where the foundational credit lies, the impact of Talk2Dino on the open vocabulary segmentation benchmarks is undeniable. It certainly sets a high bar for future hybrid architectures.
Indeed. And this work really highlights the ongoing importance of rigorously dissecting these kinds of hybrid solutions. We need to truly understand which component, is it the pre-trained foundation or is it the learned connecting layer, is really driving the success when we face the inherent complexities of these dense prediction tasks.